Okay, I promised that the impulse momentum theorem would bring us into the principle of conservation of linear momentum, and I'm going to make good on that promise right now. First, we have to define what are known as internal versus external forces. So if we have a collision with two billiard balls or any two objects, the baseball with the bat or any of those types of things, the internal forces are exerted by objects that are inside a system and on each other. Now, in this section, it's going to be very important for us to, in each case, decide what the system is. And so what we'll do is we'll draw a dotted line around whatever we consider to be inside of our system. Usually, that dotted line will include the two objects that are hitting each other. So, if I draw a dotted line around these two objects, that means that these two objects are in my system. They're under consideration. Any forces between those two objects are called internal forces. Okay, between those two objects. The external forces are forces exerted by objects outside the system on objects inside the system. So, for example, while these two guys are in contact with each other, then the one on the left exerts a big force on the one on the right. The one on the right exerts a big force on the one on the left, trying to push against each other. But there might also be gravity acting on both of them. Or a normal force, if these are two billiard balls on a table. So these forces that act from outside of the system on objects inside the system are called external forces. And these two forces between the two objects in the system are called internal forces. So that's the difference between internal and external. Nothing too fancy, really, honestly. It seems to make sense, hopefully. Derive the conservation of linear momentum from the impulse momentum theorem, as promised, assuming that the work done by external forces is negligible. So this phrase, the work done by external forces is negligible, is one that I would like for you to commit to memory. It is a condition under which you get conservation of linear momentum. Linear momentum being mv. I think I called it momentum before, but people use the word momentum and you also use the word linear momentum to describe it. We will also later on in this chapter talk about angular momentum. And so when we want to distinguish the two, we talk about linear versus angular momentum. All right, and then what we want to do is to define the total linear momentum. So if we have two objects, Object 1 and Object 2, just like in this diagram here, we have a force of Object 2 on Object 1, that's this force, and a force of Object 1 on Object 2, that's this force. And if we want to apply the impulse momentum, what we'll first do is to apply the impulse momentum theorem to Object 1. So these are the forces on Object 1. And so we'll need the mass of Object 1 to appear and the final velocity and the initial velocity of Object 1. So that's the final, this right here is the final linear momentum of Object 1, just after the collision. This is the initial linear momentum of Object 1. Perfect. And this is the, I misspoke before when I said what F12 and F21 is. This one is the force on Object 1 due to Object 2. So let me just write that out. F12 is the force on object 1 due to object 2. And we're going to be assuming a system that includes both objects. So here's object 1, here's object 2, here's our system. It includes both of them. So this force, this F12, the force of object 1 due to object 2, is an internal force. Okay, perfect. This is the average, and I should also say that this is the average, because there's a bar over the top, that means average. So this is the average force of on object 1 due to object 2. This is the force on object 2 due to object 1, and it looks the same. Instead of M2 or M1, we have M2 now. The final momentum of object 2 minus the initial momentum of object 2. Perfect. So now what we're going to do is a little trickaroo. We're going to add these two equations. And we have a delta t on both of these left sides. We'll have F12 delta t plus F21 delta t. Well, that just gets us F12 plus F21 quantity times delta t on the left side. Then on the right side, we're going to add these two terms up first. M1 VF1 plus M2 VF2. That's that. And then we're going to add these other two terms. Add a minus M1 VO1 plus a minus M2 VO2. Well, that gives us a minus M1 VO1 plus M2 VO2. So we can recognize now that we've collected together now all the terms involving the final momentum. So this is just a notational step. We're going to take this F in the subscript here and bring it outside. This just says that M1 V1 plus M2 V2, or M2 V1, V2, there's a mistake here. This should be 2. You make a note to correct slide 16. That's M1 V1 plus M2 V2 final minus M1 V1 plus M2 V2 initial. And we've just brought the 0 out in this case. So the bottom line, I know it's a lot of math, sorry about that. But notice here what kind of a miracle is going to occur. If you go back in chapter 4, concept 8, it's called Newton's third law. And what does it say? It says that the force of 1 on 2, or A on B, is equal and opposite to the force of B on A. So F21 should be the negative of F12. That's what we've said right here. F21 is minus F12. That also applies for average forces. So these two terms here, if F21 is minus F12, this is minus then minus F12. But F12 minus F12 is just 0. So the left side of this equation vanishes. It's just the prettiest little demonstration, or prettiest little derivation in the world. So the left side of this equation is equal to 0. And on the right-hand side, I get M1 V1 plus M2 V2 final minus M1 V1 plus M2 V2 initial. And since that is equal to 0, I can take this one that's being subtracted and put it over to the left side, and I get this. So this is a statement of conservation of energy. What does it say? It says that M1 V1 initially, that's the initial momentum of object 1, plus M2 V2 initially, that's the initial momentum of object 2, equals M1 V1 final, the final momentum of object 1, plus the final momentum of object 2. So that needs to be corrected also. m2v2. Well, we're just going to define the total momentum to be this capital P. Instead of lowercase p, when we talk about total momentum, we use a capital P. It's m1v1 plus m2v2. I know this is a lot of theory, and we'll do some examples here. I apologize for all the theory, but it's exciting to me. And I hope it is to you, to see the beauty of the mathematics, how it comes out here. But the beauty is that now we can write this equation here in a very simple manner. The total momentum initially, that's this, equals the total momentum finally. And there should be an F here for final. Wow. So the initial total momentum equals the final total momentum. So total linear momentum of an isolated system, meaning that the external forces can be neglected, is constant. And when we use the word conserved, like we did with conservation of energy, we mean that it's constant. It doesn't change. So during a collision, with all the ugly stuff that's going on between the baseball and that bat, if the external forces can be neglected, if the work done by external forces can be neglected, then the momentum is conserved. And we can find out some amazing bits of information from that. And an isolated system is one in which external forces are negligible. And some of you might be saying, well, hang on, Dr. Edwards, we never really assumed that the external forces are negligible. And in fact, it's right here where we assumed it. We assumed that the net force was, well, it's actually about basically here. The impulse momentum theorem deals with only with the net average force. And we assumed that that net average force was equal only to the internal force of collision. We didn't include any external forces like gravity or normal force or anything like that. So that's where we assumed that those external forces would be negligible. The work done by external forces are negligible. All right, let's state the steps for solving problems using conservation of momentum and energy. Find the stages of the problem. The first step is to identify the stages of the problem, with each collision treated as a separate stage. And I'll tell you what I mean by that with an example. And then for each stage of the problem, a stage is just a word that I use to mean segment of the problem. And there might be energy conserved during one stage and momentum conserved during another stage, et cetera, et cetera. We're going to draw a diagram, including a coordinate system and a dotted line around the objects in the system. Like we talked about, draw a dotted line around the objects in the system. And part of the trick in getting used to solving these problems is to think about what you want to include in your system. It's a free country, but boy, if you include the right objects in your system, it's almost always a lot easier to deal with that problem. All right, identify the initial and final events. Conserve energy if the work done by non-conservative forces is negligible. So when we talked about conservation of energy, we talked about work done by non-conservative forces. And if that work done is negligible, then you can conserve energy. You're going to conserve momentum if the work done by external forces is negligible. The ones that act from outside the system on objects in the system. So this is an acronym if you want one. I deem this procedure worthy of my consideration and yours. So this is a statement of conservation of energy. The initial kinetic energy of object 1, initial kinetic energy, so this O means initial, so everything on this side of the equation means initial. Initial energy of 1, initial energy of 2, kinetic energy, plus the initial potential energy of 1, plus the initial potential energy of 2. And then over here is exactly the same terms except evaluated at the final time. That's conservation of energy. These are statements of conservation of momentum. And these look a lot like the conservation of momentum statement that we had before, but now we've written them as component equations. Just to remind you, here's the vector statement of conservation of momentum. But I can always go through and take the x component of every term and then go through and take the y component of every term. So what do we get if we do the x component? Excuse me, m1v1x plus m2v2x. So this is m1v1x plus m2v2x initially equals m1v1x plus m2v2x finally. The same thing here for y. All right, conceptual example. Imagine two balls colliding on a friction-free billiard table. Is a one-ball system isolated or a two-ball system isolated? And what we mean by isolated, remember a couple of slides ago we talked about this, is that the work done by external forces is negligible. You might say, well, what do you mean by negligible? I mean, you can neglect it. You can assume it's zero. Okay? This is a dotted line. This black rectangle is a dotted line around only the left billiard ball. We've got a right billiard ball making contact with it, colliding with it. Is this system isolated? Well, is the work done by external forces negligible? If this orange ball is not included in your system, then it will exert a force that will now be external on the yellow ball. So this is an external force. That force is going to be very strong compared to any other forces, and this is not going to be an isolated system. If it's not isolated, then momentum is not conserved. All right, well, what about this case here? Now my system includes both balls. There's definitely still a force of the one. Each ball exerts a force on the other. There are other forces that act on the system. The weight of ball 2, the weight of ball 1, the normal force of the table pushing up on ball 1, and the normal force of the table pushing up on ball 2. Well, is it isolated? Namely, is the work done by external forces negligible? Well, first of all, if we could compare this collision, F12, the force of collision, with the other forces involved. Well, let's say we just put our finger between those two balls as one is coming toward the other. When they actually hit each other and collide, we're going to say, ow, that hurt, especially if somebody really gives it a pretty good hard velocity. As opposed to balancing one of those on our finger, which would give us a measure both of the gravity and of the normal force, which will be negligible compared to that force of collision. So these forces, even though normally we'll need to look at the weight and the normal force, these forces are quite negligible compared with the force of collision. There's another reason why the work done by these forces is negligible, and that is that the displacements are horizontal and these forces are vertical, either vertically upward or vertically downward, and the work done in a displacement that's perpendicular to a force is zero. So that's another reason why they're negligible. All right, let's do an example. So finally, a 54 kilogram woman, so she's 54 kilograms, and an 88 kilogram man push off against each other. they're initially stationary on the ice. So they position themselves in front of each other. They put their hands against each other, then they push off away from each other. And the woman moves away with a speed of 2.5 meters per second. So this is 2.5 meters per second for the woman. Find the recoil velocity of the man. Well, we can do that. Conservation of momentum. mv plus mv initially, but now in the x direction, with x being chosen, positive x going to the right initially. Well, what is the initial velocity? Well, neither of them are moving at all before they push off against each other. So we've got 0 meters per second for the one and 0 meters per second for the other. That's easy. We get 0 for the left-hand side. What about the right-hand side? Well, if the woman is considered to be mass 1, then her mass is 54 kilograms. Her velocity in the x direction, and in these problems it's really important to keep track of what direction you're talking about, x, y, z, whatever, plus the mass of the man times his velocity, final velocity, in the x direction. Well, we've got 0 on the left-hand side. All this stuff here adds up to 0. So we can actually solve for v2x using the principle of conservation of momentum, as long as we can ignore the work done by external forces. So let's be clear about what our system is in this case. And I think you're getting the hang of it right now. And you might say, well, Dr. Edwards, I probably want to include the man and the woman in my system. And I say, you're right. That's what you want to do. So here's the system. We've drawn a dotted line around it. Includes the man and the woman. Here's before the push-off. And here's my system after the push-off. And we might say, what forces act on the man that are external to the system, that are not internal forces between the two objects? You might say, well, hello, the weight and the normal force, and maybe a little bit of friction with the ice skates and the ice. Well, first of all, the weight and the normal force are perpendicular to the motion, and so they're not going to do any work anyway. But they can probably be neglected compared to the force of the hands pushing against each other. But, and what about friction? Well, we're on an icy surface. Probably the best justification for the work done by the normal force and gravity is not that they're small compared to the force of pushing off, but that they are perpendicular to the motion, and therefore they do no work, just like we talked about in chapter 6, I believe it was. Okay, so we're justified in saying that the system is isolated. We can ignore, we can neglect any other forces except the internal forces, and we say therefore that the system is isolated, and we're justified in writing down that momentum is conserved. Happy day. Well, now back to the task at hand. We've got a 0 left-hand side. We want to solve for x v2xf. I'm going to subtract the 54 times 2.5 over to the left side. Then I'm going to divide by 88, and that gives me this for the final velocity. Plug the numbers in, and we get a negative 1.5 meters per second. Okay, so that says that the man is going in negative, his x component of velocity is negative 1.5 meters per second. Now, I might ask, if the man is heavier than the woman, which he is, more massive than the woman, why should his velocity be slower? First of all, why is this negative? Now, the negative says nothing more or less than the fact that this velocity is in the man's velocity is in the negative x direction. X is to the right, his velocity is to the left, and so the minus sign says no more or less than that. No big deal. But why is this smaller than the speed of the woman? Well, you might think of taking this to the absurd limit where you've got a huge 400-pound man on the ice, and she pushes against him she's going to go flinging back pretty fast. I mean, I think our own gut intuition would tell us that she's not going to be pushing him around very much, but she's definitely going to push her around a lot, given his much greater mass. And that's reflected here. The man is more massive, and his velocity at the end of the collision will be less than that of the woman. Now, if they'd both been the same mass, then they both would have come off at the same speed.